Okay, so in our last video we were discussing two main techniques, direct methods and iterative methods, for solving the systems of equations. Remember, this is step 3 of the numerical solution procedure. And we're going to focus our attention on iterative methods as they're more generally applicable to large systems. They can be applied to nonlinear problems as well, and so that's the most popular technique. So we're going to focus on Gauss Seidel, which you'll remember from the 1D case. This section number should be just 3.4, not 44. So you can change that. So remember, we talked about Jacobi, Gauss Seidel, and SOR. Each was an improvement on the previous one for various reasons. And we're going to focus on Gauss Seidel here and show how it would be applied to our Poisson equation. So if you remember from last time, here's our difference equation for the Poisson equation. I've just rewritten it. The only difference is I've rewritten the delta x over delta y squared. I've rewritten as delta bar just for shorthand there, but this is the same difference equation that we had before with the 1, 2, 3, 4, 5 unknowns. And so we're going to apply the Gauss Seidel iterative method, a simple technique that we'll apply over and over and over again to iterate or relax on the solution as it gets closer and closer, iteratively converges to the correct solution. So if you remember the Jacobi method, we simply solve for the uij term. So here we have our 5 unknowns, and we just take the ij term at the middle of our stencil, 5-point stencil, and we solve for that. So it's an explicit expression for uij in terms of all the other points. So our 5-point stencil, 1, 2, 3, 4, 5, like this. The Jacobi method, we solve for the ij point at the center in terms of the 1, 2, 3, 4 points surrounding it. So on the right hand side we have the ui plus 1j, ui minus 1j, uij plus 1, uij minus 1, and of course the fij. So we just solve for this point at the center of the stencil. Remember that the superscript in parentheses here indicates the iteration number. So everything on the right-hand side is n, indicating taking from the previous iteration in order to get the n plus first new iterate, the new approximate solution. So in the Gauss Seidel method then, the improvement was to recognize that as we sweep through the grid, for example, if we're sweeping from left to right in x and from bottom to top in y, what we're recognizing is that these 2 points have already been updated when we get to the ij point. So the I minus 1j point and the ij minus 1 point have already been updated. So Gauss Seidel takes the same finite difference equation as we have here, but rather than just having all 4 of these on the right-hand side at the previous iterate, we recognize that the I minus 1j and the ij minus 1 values have already been updated, so we use the most recently updated information on the right-hand side. So it's the same equation as Jacobi, just using the most recently updated information as it becomes available. Now you'll remember from our discussion for the 1D case that we don't actually program it any differently. We don't identify specifically whether it's an n or an n plus 1. We just keep everything in the same 2-dimensional array now, and so if a point gets updated, it's updated, and if you pull out that point to do another calculation, it's the most recently updated value. So there's nothing that in the code that says whether it's an n or n plus 1. Okay, so the procedure is very straightforward. It's just like the 1D case, it's just now in 2 dimensions. So we start with an initial guess, n is equal to 0. We update all the points, all the ij points throughout the 2-dimensional grid. And then as we relax, as we iterate, we get the first iterate, the second iterate, third iterate, and on and on and on until it converges. And the convergence test is exactly like before, it's just now 2 dimensions. So remember, we walk through why this is a good convergence test. So we take the maximum of the absolute value of the difference between the new and the old iterate and divide by the maximum of the absolute value of either the new or the old. I showed the new here, it doesn't really matter. And then when that is less than epsilon, value that we specify, then we say the iteration process has converged. So boundary conditions, this is going to parallel exactly what we did in the 1D case. So you'll see a lot of similarity there. It's just 2 dimensions instead of 1, which really only adds in 1 extra complexity, which we'll see. But for Dirichlet boundary conditions, just like in the 1D case, you put in the values along the boundary as they're given to you from the boundary conditions. So u1j, ui plus 1j, ui1, and ui cap j plus 1 are all known, and those you just put in on the boundary, and you only iterate on the interior points, 2 to I and 2 to j. So for example, what happens is if you are in the lower left-hand corner, so if you're at the 2, 2 point, so you're at 2, 2, I is equal to 2, and j is equal to 2. So if you're at the 2, 2 point, which is right here, then the 5-point stencil includes a point above, a point to the right, a point below, and a point to the left. So now when you apply that same Gauss Seidel equation that we had on the previous slide, at the 2, 2 point, you'll notice 2 of the points are on the boundary. So the u12 and the u21 are on the boundary. Those values are known, and so we don't have to calculate them. So this is this point right here, and this is this point right here. So those values are just picked up because they're known. You don't have to do the coding any differently. You already put them in to the boundary values, so they just get picked up by the equation. All right, so Dirichlet boundary conditions are very simple, very straightforward, just like in the 1D case. Neumann boundary conditions will follow the same basic approach as we did in 1D. So let's say we have that partial u partial x is equal to c at x is equal to 0. So x is equal to 0 is the left boundary of the domain. And then we're going to specify the normal gradient partial u partial x along that vertical boundary. Now, we didn't go through this in the 1D case. I'll just quickly go through it here. Just because some of you may think of this, and it turns out not to be a good idea, but let me just walk through it and argue why this is not a good idea. So the first thing you might think of is, well, why not just use a forward difference approximation for this first derivative and use that as our boundary condition? So if you did that, this is what you'd have. You'd have u2j minus u1j over delta x is equal to c. Of course, that's only first order accurate, which is what I want to emphasize here. But just follow the logic. So you could then solve this for u1j, which you could then update along that x is equal to boundary based on the interior points, which include the u2j. The problem with this, and the reason why this is not acceptable, is because it's only first order accurate. You say, well, but it's just the points along the boundary, everything else is second order accurate. That's true, but remember that the order of accuracy not only affects the error of the values themselves, it also influences and determines the rate of convergence of the iterative process. So, and what happens in practice, unfortunately, is if any one of your portions of the domain only converges at a first order rate, then the whole thing gets bogged down. It basically goes to the least common denominator. So even though most of the domain is being updated using second order techniques, just because we have a first order technique along one boundary will typically kill our convergence rate. So because of that, we do not do that. That is not the best approach. Instead, we do the same thing as we did in the 1D case. So if you remember in the 1D case, it's the same idea. It just looks more complicated here. So the first thing you do, it's a two-step process. So the first thing you do is you apply your difference equation at the boundary. So I'm going to apply it at the left boundary when I is equal to 1. So this is exactly like we had before, but I is equal to 1. So we have 1 here, 2 here, 0 here, 1, 1, 1. Now I've highlighted in red the problem point. It's the same issue that we had at the tip of the fin in the ordinary differential equation case. So this point is outside the domain. So if you do your 5-point stencil, the domain boundary is now actually along this line. And therefore this point, so this is I is equal to 1 here. So this point is I is equal to 0, which is outside the domain. So we need to eliminate that point. And we'll do it exactly the same way we did in the 1D case. So we've applied the finite difference equation at the boundary, which gives us this point outside the domain. Then we take the boundary condition. We use second-order accurate central differences to approximate its derivatives, which here you have on the left-hand side. And that also involves the point outside the domain, because we used a second-order accurate central difference at the boundary. So we can solve this for u0j, which I've done here. u0j is just u2j minus 2c delta x. Remember, the c is the specified flux, or the specified gradient of u. And now we substitute this uij into here to eliminate it. So in place of this, we're going to put this. And now everything is known. So when we do that, we get this as our expression for the difference equation at u1j. So that's along that left boundary when I is equal to 1. So we have a version of the difference equation applies in the interior, and now we have a separate version, which has been particularized for the left boundary. And so you just sweep along that left boundary. I is equal to 1, j is 2 to capital J, and use this equation to update those boundary values. Okay, some comments. So this is basically the same procedures we just had for the Dirichlet boundary condition case, but we just have one additional sweep along that left boundary. And we can apply the same approach adapted to Robin boundary conditions, which is what we did in the 1D case. We can do the same thing here in the 2D case. It works exactly the same. Now, where things do get a little bit more complicated in the 2D versus the 1D case is the following. So what would happen if we had that left boundary condition, Neumann, but let's say we had a Neumann boundary condition along the top boundary as well. So that would be partial u partial y, normal derivative, is equal to some specified value d. So that's along the top boundary. So now we have, let's draw it. So now we have the top left corner of our domain looks like this. So this is this point is j, let's do it this way. So this is I equal 1 and j equal capital J plus 1. Okay, this point right in the corner. So we have then partial u partial x is c along this left boundary, and along the top boundary we have partial u partial y is d. So what we just did in the previous slide was look at values along points along that left boundary. What is the difference equation we use to update using Gauss Seidel? Now the question is, if we also have a Neumann boundary condition along the top, then we also have to evaluate these points along the top as well. So let me extend this up. So we're going to have a fictitious point up here. We've already dealt with, let me just drop here. We've already dealt with the fictitious point out here. Let me do it this way. J is capital J plus 1. So we've already dealt with this fictitious point here, because that's the same as along this left boundary. So now we need to deal with this one. So to get the points along the top would be the same as the points along the left, do exactly the same process. But now what about this corner? Because for the corner we have to eliminate both this point and this point. We've already eliminated this point. Let's now eliminate this point. Okay. So here we go. So here's our difference equation along the left boundary, but applied at I is equal to 1 on the left boundary, and little j is cap j plus 1, which is the top boundary. So this is that upper left-hand corner. So this is just one point, that upper left-hand point. And you'll notice right here, there's the j plus 1 term, which is now capital J plus 2. That's the one that I indicated here, right here, is outside the domain. That is capital J plus 2. So we do the same thing. We take the boundary condition along the top, use a second order accurate central difference approximation for its derivative. We have the point outside the domain. We solve for that, and we substitute into our difference equation. And remember, this version already has taken care of that left boundary. So now we just substitute this to take care of the upper boundary as well. All right, so that's what gives us this expression here. This only applies at that upper left corner. Just that one point we have a separate equation for. So things can get pretty messy. So if you had, for example, Neumann boundary conditions all the way around, then you'd have, let's just count how many different Gauss Seidel equations we have. We have one for the interior, we'd have one for each of the 4 boundaries, and then one for each of the 4 corner points. So that would be 4, 8, 9. 9 total equations, some 1 for the interior, 4 for the boundaries, and 4 just for the corner points themselves. Let's just take a quick look. I'm not going to go through all the details, but this is solving Laplace's equation for the temperature distribution, because Laplace's equation we discussed beginning of chapter 7 is the governing equation for heat conduction, two-dimensional heat conduction. So let's just show the solution of Laplace's equation with Dirichlet boundary conditions all the way around. So what this says is that u is equal to 0 on the left, bottom, and right boundaries, and 1 along the top. And what you get is this. So this is a contour plot of the numerical solution. So here's the x direction, y direction, and then we have 1 by 1 domain. We have u is equal to 0, 0, and 0 along the 2 vertical sides in the bottom, and then 1 along the top. And if you plot the contours, these are contours in increments of 0.1, so this one is 0, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, 0.9, and 10 would be along the top, 10 meaning 1. So that would be a plot of the temperature. These are isotherms, so it's 0 here, 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8. So you get up to 1 along the top. Okay, so you can now do problem set number 7. Problem set number 7 is all based on finite differences and boundary value problems, and that'll be the last problem set for the semester.